In this demonstration, you'll learn how to set up a steady-state thermal simulation to study the distribution of temperature in the model when a heat flux, a convection, and a radiation are applied. I'll start by selecting a simulation process template from the study panel on the left here. I'm going to select the thermal template. I'll select the option to define new geometry. I am running a pure thermal simulation, so I won't select another physics type. I'll accept the default selection for the options list so that contacts in the interface of the bodies are detected automatically. I will then apply the template and create the simulation process. In creating my simulation process, the first thing that I'm asked to do is define my geometry. So I'll select the geometry task. There, I'll choose to import a geometry file. I'll select the geometry file for the curved three-part pipe. AIM will now load the geometry and apply additional tasks that are part of template setup. My physics task, the red exclamation mark here, is telling me that the physics task needs more information added in order to complete the simulation. I'll click on it to go into the physics task. You'll see that a lot of defaults have already been set up for me. Material assignments, physics options, interface conditions, and solver settings. You can also see that an interface generator has been created, and contacts will be generated when this task is updated. The blue button shows the actions that still require attention. Here, I need to add some boundary conditions. First, I'm going to add a heat flux to the face of this exposed cross-section. I'll use the face selection filter to select the face. Then I'll add the heat flux boundary condition from the context menu. I enter the magnitude of this boundary condition and press Enter. The boundary condition should now be up to date. Note that the heat flux value is also shown here in the heat flux panel. Next, I want to apply a convection to the inner curved faces of all of the three bodies. I'll start by selecting the three outer faces and hiding them. Now, I'll select the inner curved faces of all three bodies. Then, I'll right-click to add a convection boundary condition. I'll enter values for the heat transfer coefficient and the convection temperature property and press Enter. You can see that these values are also reflected here in the convection panel. I now want to add a radiation boundary condition to the outer faces of the three cylinders. First, I'll want to show all bodies again. Then I'll select the faces and right-click to add a radiation boundary condition. I'll enter values for the emissivity and radiation temperature properties and press Enter. I am now finished with my boundary conditions. And with these few additional settings, my physics solution task is all set up. Now, I'll update the physics solution task by right-clicking it in the workflow view and selecting Update. Because the meshing task was also ready to go, it will be automatically updated first. Once the meshing task is done, AIM will move on to update the physics solution task. Everything's up to date, so now I can view my results. I'll click on the Results task. And then Evaluate. The template has already inserted one contour result for temperature. This shows the distribution of the temperature throughout the model. This concludes this demonstration of an end-to-end basic steady-state thermal analysis in AIM.